Hello, this is chapter 16.1. This is a new chapter now on vector fields. We are going to transition to vector fields until the end of the course. So far this course we have only talked about scalar fields, so those are scalar functions that assign a scalar quantity to every point in 2 or 3 dimensions. Scalar quantities are things like the mass or the density or the temperature. We're transitioning now to vector quantities to model things like velocities and forces. So there's two different types of vector fields, two-dimensional and three-dimensional. So a two-dimensional vector field is a function that assigns every point xy in the plane to a two-dimensional vector, again in the plane. So this is written as a function of xy, and the output of the function is a vector, so that's why there's a little vector on top here, and I'm using the column notation here for the vector whose components are p of xy and q of xy. So p and q independently of one another are scalar functions, but when you put them together in the form of a vector, this whole thing becomes a vector function, or also called a vector field. So it assigns every point xy to a vector pq. So if you have a point whose coordinates are x and y, this gives you the point x, y. This function is going to take this point as an input and is going to give as an output a vector whose components are p, q. So the vector may look like this, and this is the vector p, q. And the components of this vector are p and q, where p is the projection in the x direction, and q is the projection in the y direction. So I'm writing pq as a column vector. You can also write pq as a vector in brackets. Or you can also use Hamilton's notation, p times the unit I vector plus q times the unit j vector. These are all equivalent notations for the vector. It's just important not to confuse the point xy with the vector pq. xy is the input, pq is the output. You can do the same thing in 3 dimensions. In this case, the function takes as its input a point in 3 dimensions whose coordinates are x, y, and z, and the output is now a vector in a 3-dimensional vector with 3 components, p, q, and r, each one of whom is a function of x, y, and z. So you take a point x, y, z, and you map it to a vector p, q, r. So for an example, let's start with a 2-dimensional vector field. F of xy equals x minus y, x. So to get an idea of what this looks like graphically, we need to build a table of values. So for inputs, we need to choose pairs xy. And for every pair xy, we're going to get an output, which is f, the vector f. So we can take a grid of points. I'm going to choose a grid of 9 points from -1 to 1, stopping at every integer in x and y. -1, -1, 0, 1, -1, 0, 1, 0, 0, 0, 1, 1, 1. So you see these 9 points here are 9 points located on a grid in the xy plane. From -1 to 1. You can go much further, but it takes a long time to do this. So I'm just only taking 9 points around the origin. Now each one of these 9 pairs of points xy I will plug into the function. So if you have x equals -1 and y equals -1, when you plug them in here, the result is the vector 0, -1. Which you can go now to the point -1, -1, which is this one right here, and plot the vector 0, -1 starting at this point. So 0 in the x direction and -1 in the y direction is a vector that looks like this. So the next vector, 0, -1, you plug it into the function. The result is the vector 1, 0, which is 1 in the x direction and 0 in the y direction. The next vector gives you 2, 1, and that's at the point 1, -1 right here. The vector goes 2 in the x direction and 1 in the y direction and looks like this. And you can go down the table. So the next vector is -1, -1. The next one is 0, 0, 1, 1, -2, -1, -1, 0, and 0, 1. So this next vector, -1, -1, at this point looks like this. At the next point, the origin, the vector is the 0 vector, so there's no vector in the middle. 1, 1 for the next point up here. -2 and -1 for the next one. -1 and 0. So back 1 in the x direction. And 0, +1 for the next point up here. Okay, so we see the general aspect of this vector field is that it's a rotational vector field, so it rotates around the origin with a counterclockwise orientation, and the arrows get bigger as you move away from the origin. So you can visualize this as, for example, a velocity or a force field in a two-dimensional space, like a pool of water where this would be the water currents or the air currents, or the lines of force in a magnetic or an electrical field. So this can be done much more efficiently with a computer. A computer can take many more points than just 9 and plug these in and plot this very quickly and very efficiently. So I'm going to do that with MATLAB. And this is what it looks like. So here you have many more points, and you can see much better this rotational aspect of the vector field. You can do this with MATLAB, like I said, or there's a variety of tools, free tools on the internet, just websites where you can just plug in a vector field and hit plot, and plot the vector field that way. So I'll put the reference to those websites on Schoology in case you want to do this on your own. So to look at a couple more examples, a little bit more complicated, f of xy equals cosine of x plus 3y over x minus y. So this would be a difficult one to plot by hand like we did the one above, but if we plug it into MATLAB, this is what we obtain. So you see this has much more complicated aspect. You have velocity or force lines going upwards on the right and downwards on the left. And along this diagonal, you have these little whirlpools that kind of rotate counterclockwise at different intervals. As another example, f of xy, if you take x squared minus y squared minus 4 and 2xy. So again, this can be done easily with a computer. And this is how this vector field looks. So this is a typical vector field that you see in physics when you study magnetic dipoles. These are the lines of force that are observed between the north and the south pole of a magnet, for example. So moving on to three-dimensional vector fields, the concept is the same. F of xyz equals x plus y, x plus z, y plus z. So in order to plot this, you technically would need to take a grid in three-dimensional space that uses triplets x, y, z. At each one of those points, you plug in the components into this function to get a vector, and this is now a three-dimensional vector. So this becomes very difficult to do by hand, but with a computer it's possible to do it easily. And this is what this looks like. On MATLAB you have the option of rotating the view to see it from different directions. So the blue vectors have different orientations depending on where they are evaluated. If you do look at them from above, you see that this is a rotational vector field that goes clockwise this time. All the arrows go around the z-axis clockwise, but if you look at them from a different perspective, you see that they also have a vertical component in addition to the horizontal component. So as I mentioned, you have several applications, especially in physics. So you have force fields or velocity fields. V of x, y, z, where you can have velocity field of so an air or water. Force fields, and depending on the force, it could be a gravitational force field, G, or it could be an electric or magnetic. These are the letters that are used for gravitation, electric field, and magnetic field. So there is one type of vector field that everyone has already seen from Calculus 2. These are gradient fields. And these are vector fields that are created by taking the gradient of a scalar function of multiple variables. So if we go back to a scalar function, so little lowercase f of xy, which means that its output is simply a scalar. So you can build a gradient field called the gradient field of f by taking its gradient. So capital F of xy equals the gradient of f at xy, and the gradient of f is a vector whose components are the partial derivatives of f with respect to x and y. partial derivative of x, and partial derivative with respect to y. This is a definition of the gradient, which you can also write in simplified notation with the subscript f xy and f subscript y xy. So, for example, if you take the function f of xy equals x squared minus 1/2 y cubed plus 4, so this is a scalar function. The gradient field associated with this scalar function is the vector function f, capital F of xy, equals the partial derivative of this with respect to x, which is 2x, and the partial with respect to y, which is minus 3/2 y squared. And this is called a gradient field, which is a vector field. So there are many ways to flip back and forth between scalar functions and vector fields. There's a close relationship between these two kinds of functions, and we'll see there are many theorems and shortcuts that you can use by using one instead of the other depending on the application. So as a reminder, the gradient field has several properties. So first of all, the vectors, the gradient vectors, always point in the direction of steepest increase. So this implies that these vectors are perpendicular to the level curves. The level curves of f. And the magnitude of these vectors is equal to the steepest slope, or the steepest directional derivative in the direction of the gradient. So the steepest slope, which is also called the directional derivative. So, for example, if we were to plot the gradient field of the scalar function in the example above, again, if I use MATLAB to do this, we obtain this figure right here. So these arrows are the vector field, the gradient field, and here you have these curves, which are the level curves of the function little f. So as you can see, the gradient vectors are always perpendicular to the level curves, no matter where they are. If we look now at the function itself in three-dimensional space, so the function looks like a surface, the function f of xy, and you can see that these gradient vectors point always in the direction of uphill increase on this surface, and that the larger the vector, the steeper the slope is when you are on the three-dimensional surface. Okay, for this course primarily you will have to be able to recognize gradient fields, not necessarily plot them.